Today we are going to study the method of action angle variables. This is a method used to find the period or frequency of periodic systems without finding the complete solution. There are actually two types of periodic motion. One is libration or oscillation and the other one is rotation. Libration, you all know about the libration or oscillation, that is the oscillation of a simple pendulum. So we can represent the phase diagram of liberation like this. This is a phase diagram for liberation, and for rotation we can represent the phase diagram like this. That is, the q or the theta variable is continuously changing with respect to time. But in the case of liberation or the oscillation, the q it takes the value of the initial position after some time or the period. Let us briefly discuss how to find the period or frequency of this type of periodic motion with the help of action angle variables without finding the complete solutions. Let us consider the time independent Hamiltonian of a one-dimensional periodic system be h as a function of q and p, and let it be equal to a constant alpha 1. From this expression you can simply see that this p is a function of q and alpha 1. Let me integrate this p over one period and take it as j. Integral p dq. This closed integral represents the integral over one period of motion. This is one period, or in this case this is one period. So this is the integral of momentum p over one period. Let me ask you, is this j is a constant? Actually this j is a constant. We can show that. Let us substitute this p here. That gives j is equal to integral, the closed integral over one period p as a function of q and alpha 1 dq. Here this integral is actually a definite integral, and the integration is performed over the q variable. So we can simply see that this RHS is only a function of the alpha 1 itself. So we can write that this j is a function of alpha 1, because during integration the q variable integrates out. From here we can say that this j is only a function of a constant alpha 1. So this j is constant because this alpha 1 is a constant. From this relation we can inverse this relation and write this alpha 1 as a function of j. From our old classes we know that the Hamilton's characteristic function w is a function of the old variables q and the new momentum alpha 1. So if we substitute this alpha 1 here, what we get is this characteristic function w as a function of the q's and the j's. We can find the conjugate variable corresponding to this j by taking the partial derivative, that is dot w by dot j, that gives the conjugate variable corresponding to this j. Let me denote it by the omega, the letter omega. Actually this omega is called the angle variable. this omega is called the angle variable, and this j is called the action variable. In fact, this omega and this j are the canonically transformed coordinates from the old phase space variables q and p. That is, q and p are the old phase space variables, and we apply the canonical transformation and we get the new phase space variables omega and j. Let me ask you, which generating function generates this canonical transformation? In fact, the generating function which generates this canonical transformation is actually the Hamilton's principal function S. We have the new phase space variables omega and j. So let me ask you, what are the new Hamilton's equations in this new phase space? The new Hamilton equations are omega dot, which is equal to dou omega by dou t, which is equal to dou h by dou j, and the other Hamilton equation is j dot, which is equal to minus dou h by dou omega. These are the new Hamilton's equations. Let me take this omega dot as mu. This is the central idea of action angle variables. Now our target is to show this mu is the frequency of the periodic system. If we are able to show this mu is the frequency of the periodic system, that implies we can simply find the frequency or period of a periodic system by taking the partial derivative of the new Hamiltonian with respect to j. So we don't have the need to go for the complete solution to find the frequency or period of the system. We just need to take this derivative of the Hamiltonian with respect to j. So before that, you should write our old Hamiltonian in terms of j. Otherwise, you are unable to take this partial derivative. So now let me show you this mu is actually the frequency of the periodic system. Let me show you that. Let us consider the change in the angle variable omega when q goes through a complete cycle. So we can write this change delta omega is equal to and this dq, the change in the dq is over a complete cycle, or this closed integral is taken over a period of the periodic system. And we know that this omega is actually the partial derivative of the characteristic function with respect to j. So we can substitute that here. That gives is equal to dou w by dou q dq. We can take this partial derivative with respect to j outside the integral because the integration is performed over the q variable. So that gives dou by dou j and we know that this Hamilton's characteristic function w is a function of old coordinates q and the new momentums alpha. And in our case, we replace this alpha as a function of j. So in this particular case, this characteristic function is a function of coordinates q, old coordinates q, and the new momentums j, new action angle variables j. So if we take the partial derivative dou w by dou q, that gives the corresponding conjugate variable, which is the corresponding conjugate variable to the old phase space coordinate, that is actually the old phase space momentum p. So if we substitute this old phase space momentum p here, that gives dou by dou j integral p dq. And we already know that this closed integral p dq is actually j. So this is actually dou j by dou j, and that is equal to 1. Just take a look here. Dou omega by dou t is actually mu. So from these two equations we can write omega is equal to mu t plus a constant beta. Just integrate it. Integration gives omega is equal to mu t plus a constant beta. From this equation we can take the change in omega. So the change in omega, delta omega is equal to mu delta t. Just taking the differential on both sides. Differential on this LHS is delta omega. If mu is constant, then differential on this RHS is just mu times delta t, and the differential of beta is actually 0. So if this delta t is one period, that is the period of the periodic system, so let me denote it by the letter tau. Let this delta t is tau, then this delta omega is mu times tau. So this change delta omega represents the change in the angle variable omega over the one period tau, and from this equation also this delta omega also represents the change in the omega over the one period. This is the integral over one period. This closed integral is integrated over the one period. So these two equations are actually same. So we can write this change in the delta omega, that is actually 1. The change in omega over a period is actually 1 from this equation. So we can write this 1 is actually equal to mu tau. And from this equation we can write this mu is equal to 1 by tau. We already said that this tau is the period of the periodic system. So we can say that this mu is actually the frequency, because this mu is 1 by 2. We already know that 1 by time period is the frequency of a periodic system from our school days classes. So the conclusion is we can simply find the period or frequency of a periodic system by using the technique of action angle variables. So the technique of action, using the technique of action angle variables, you just need to simply take the derivative of the new Hamiltonian, and this new Hamiltonian is written as a function of j's with respect to dou j, and that gives the frequency of the periodic system, and this is the conclusion. And the advantage is you don't have the need to go for the complete solution to find the frequency of the periodic system. So this is a very useful tool. You will get a more clear idea about the action angle variables on doing an example. So in our next class we will try to find the period and frequency of the harmonic oscillator by using the method of action angle variables. So thank you.